In Lab 5, we've modeled Faraday's law by dropping a bar magnet through a tube of aluminum foil. This represents a magnetic dipole falling through a solenoid. Using what we've learned about magnetic fields, induced currents, and magnetic forces, we created a computational model to represent our observations. We determined the direction and magnitude of the magnetic and net force on the bar magnet. Some important background information to note. We know that concentric conducting rings create a solenoid. We have learned about the Biot-Savart law for magnetic currents of infinitesimally small length. We know the relationship between magnetic flux and magnetic field. And here are some key equations that we will input into the model. My observations for the time in the tube were all very similar. The average was 1.8 seconds spent in the tube. Using our observations and the key equations listed previously, we inputted the magnetic field of the dipole using our code from Lab 3. Then we calculated the magnetic flux at each iteration of the tube, represented as the variable ring. We know that the magnetic flux changes over time, so it is important to iterate through many rings of the solenoid. We defined a variable b at ring by calling the function to compute the magnetic field of the dipole. Then we compute the magnetic force on the ring using the equation F equals I times L times B. The net force is the sum of the magnetic force and the force of gravity. The computational model produces this result. We see a bar magnet falling through the tube and the color of the tube changing as this happens. The velocity versus time graph shows the magnet falling downwards with increasing speed up until the point when the magnet enters the tube, and the magnetic force slows the speed of the magnet until the magnet departs the tube and the speed increases again. It is interesting because the computational model shows a time in the tube much less than what I observed. This could be due to inconsistencies in the estimation of the magnet's mass or in the number of rings in the solenoid. It is mainly important that the velocity versus time graph and the model reflect what we know about magnetic fields and magnetic forces. We conclude that when the tube is red, the current is moving in the counterclockwise direction when viewed from above. Because dB dt is in the negative y direction, so negative dB dt is in the positive y direction. Using the right-hand rule, we determined that the current must flow counterclockwise. When the magnet is flipped so that the other pole enters the tube first, the conclusion would be the same, because dB dt would still be in the negative y direction, and thus the corresponding currents and colors would still be the same. Based on our graph, we can determine that the magnetic force in the positive y direction causes the magnitude of the net force to decrease, although still in the negative direction. This makes sense because the magnet is accelerating downward when in freefall, so the velocity should be increasing in magnitude. But with a smaller magnitude of net force, the acceleration will have a smaller value and the velocity will decrease. If the conductor were to have nearly zero resistance, the force on the bar magnet would increase because the change in magnetic flux is equal to the EMF, which is equal to current divided by resistance. Thus, as resistance decreases and approaches zero, the current will increase. The equation for magnetic force shows us that as the current increases, so will the magnitude of the magnetic force. If the tube of aluminum foil had holes in the side, the current would have smaller magnitude because a break in the conductor would not allow current to flow.